I'm Hyacinth May Capino, and for this video, I will be discussing 3 problems from Chapter 27, Magnetic Field and Magnetic Flux, as a requirement in electromagnetism for teachers. So problem number 1 is from item 27.12, and this one deals with magnetic field lines and magnetic flux. So the problem is, a horizontal rectangular surface has dimensions 2.80 centimeters by 3.20 centimeters and is in a uniform magnetic field that is directed at an angle 30 degrees above the horizontal. What must be the magnitude of the magnetic field to produce a flux of 3.10 times 10 to the negative 4 Weber through the surface? Given the dimensions of the area, which are equal to 2.80 centimeters and 3.20 centimeters. These will then be converted into meter, and therefore we will have 0.0280 meters and 3.0320 meters. We also have the magnetic flux, which is equal to 3.10 times 10 to the negative 4 Weber, and the angle. In this part, we are actually asked to find a complementary angle of 30 degrees, and that is equal to 60 degrees. So in order to find the magnetic field, we need to use the original equation, which is the magnetic flux is equal to the magnetic field multiplied by the area cosine theta. And after manipulating the equation, we will have the magnetic field is equal to the magnetic flux all over the area cosine theta. And by substitution, we will get the value of the magnetic field, which is equal to 0.692 Tesla. The next problem is from item 27.24, and this one has an average difficulty. This particular problem discusses motion of charged particles in a magnetic field. The problem is, a beam of protons traveling at 1.20 kilometers per second enters a uniform magnetic field traveling perpendicular to the field. The beam exits the magnetic field, leaving the field in a direction perpendicular to its original direction, as seen in figure E27.24. The beam travels a distance of 1.18 centimeters while in the field. What is the magnitude of the magnetic field? Given the speed, which is equal to 1.20 kilometers per second, we also have the distance traveled, which is equal to 1.18 centimeters, the mass of the protons, which is equal to 1.67 times 10 to the negative 27 kilograms, and of course the charge, which is equal to 1.60 times 10 to the negative 19 coulombs. In order to find the magnetic field, we will use the original equation S is equal to R theta, wherein S is the arc length, R is the radius, and theta is the angle. Now we have to manipulate this equation in order to have R is equal to S all over theta. By substituting the required values, we will have the value of the radius, which is equal to 0.751 centimeters or 0.0051 meters. Using this value, we will be able to find the magnetic field from the original equation. R is equal to the mass multiplied by the speed all over the charge multiplied by the magnetic field. And using derivation, we will get the value of the magnetic field, which is equal to the mass multiplied by the speed all over the charge multiplied by the radius. So by substituting all the values, we will obtain the magnetic field, which is equal to 1.67 times 10 to the negative 3 Tesla. For the last problem, we will use the same figure as our problem number 2. this problem is from item 27.32, which deals with applications of motion of charged particles. So, in the Bainbridge mass spectrometer, as seen in figure 27.24, the magnetic field magnitude in the velocity selector is 0.510 Tesla, and ions having a speed of 1.82 times 10 to the 6th meter per second pass through undeflected. Part A. What is the electric field magnitude in the velocity selector? Part B. In the separation of the plates, if the separation of the plates is 5.20 millimeters, what is the potential difference between the plates? So, the given is, or are, the speed, which is equal to 1.82 times 10 to the 6 meter per second, the magnetic field, which is equal to 0.510 Tesla, and the distance, which is equal to 0.00520 meters. We need to find first the electric field, and in order to do this, we only have to multiply the speed with the magnetic field. So, by substituting the values, we will obtain the electric field, which is equal to 9.22 times 10 to the 5th volts per meter. Next is the potential difference. And to find the potential difference, we need to multiply the electric field by the distance. And by substituting the necessary values, we will obtain the potential difference, or the voltage, which is equal to 4.83 kilovolts or 4,830 volts. So that's it for our chapter 27 problems. If you have any questions, feel free to email me at hyacinth_cognino@dlsu.edu.ph. Stay safe. Bye.